The next thing we want to talk about is another test. This test is called the second derivative test. And what this test does is it gives us a second way of finding relative maximums and relative minimums. So what you'll notice is we know these are critical numbers or critical points because if I look at this, I see that the slope at each one of these points is equal to 0. So the first derivative is equal to 0. Now what I'm going to notice is at those points, it's concave down. So I could tell that this is a relative maximum if I were to take the critical number and put it into the second derivative. What I should find is that the second derivative is negative. If I were to take this other critical number and to put it into the second derivative, I should get a positive number because it's concave up there. This just gives me a second way to determine relative maxes and relative mins. So these ideas motivate the second derivative test. Let f double prime, or the second derivative, exist on some open interval containing c. And let f prime of c equal 0. That just means that at c we have a critical point. If f double prime of c, or when we put c into the second derivative, we get a positive number, then f of c is a relative minimum, because that tells me that it's concave up. On the other hand, if we put c into the second derivative and we get a negative value, then f of c is a relative maximum, because then we know that the graph is concave down. So this gives me a way where we're not using the number line of distinguishing between a relative minimum and a relative maximum. The only downfall is that if I put c into the second derivative and I get 0, then it doesn't tell me anything. Then I have to go back and use the first derivative test. So let's use the second derivative test and find the relative extrema of f of x equals x cubed minus 12x. So I need to find my critical numbers. Then I'm going to take those critical numbers and put them into the second derivative. So the first derivative of x cubed minus 12x is 3x squared minus 12. And I'll go ahead and factor out a 3 from each of the terms. That gives me 3 times the quantity x squared minus 4. Since this is a difference of perfect squares, I'll factor it one more step to 3 times the quantity x minus 2 times the quantity x plus 2. If I go ahead and set that equal to 0, I'll see that x minus 2 is equal to 0 at 2. X plus 2 is equal to 0 at negative 2. So there are my critical numbers, and for me to decide whether those are relative maximums or relative minimums, I need to put it into the second derivative. The second derivative is just the derivative of 3x squared minus 12, and that's simply 6x. If I put the critical points into that, I get f double prime of 2 is positive 12, so that tells me that we're concave up. If I put negative 2 into the second derivative, 6 times negative 2 is negative 12, so that tells me at negative 2 we're concave down. So at the critical number x equals 2, the function is concave up, so the critical point is a relative minimum. At the critical point x equals negative 2, the function is concave down, so the critical point is a relative maximum. Where this is going to come in handy is if you want to avoid using your first derivative test, which means testing the first derivative along the number line. But if this test fails, you're always going to have to fall back and go back to that number line. And it fails if you get either one of these numbers here coming out to be 0 from the second derivative.